Okay, hello everyone. In today's class, we will discuss sequence to sequence modeling, right? And we'll also start attention. So, in the last class, we discussed RNN methods, advanced RNN methods, LSTM, GRU, and so on and so forth, right? We have seen how gating mechanism can address the vanishing gradient problem, right? We will see how RNN can be used in the other types of problems like sequence to sequence labeling problems, right? Before that, today's breaking news. Can you guess what is going to be today's breaking news? Yeah, so Gemma 2 billion released, right? And this is one of the smaller language models proposed by Google, right? 2 billion model. This is essentially a distilled model from the bigger Gemini version of it, right? And it was also shown to be very effective in safeguarding some of the toxic content, right? So they also released this Shield Gemma, right, which is basically a suite of safety content classifier models to filter the input and outputs of AI models and keep the user safe. Okay, so you can use this. Gemma 2 billion already suppresses some of the larger models like GPT 3.5 Turbo, Mixtral. Mixtral is different model, by the way. Okay, don't mix up with Mistral. Llama 2 70 billion, and then other models also. Okay, let's get started. So, sequence to sequence models. We are discussing those things which were proposed in 2015, 2016, right? Right. So in sequence to sequence model, what is a sequence to sequence problem? A sequence to sequence problem is you are given a sequence and the output would also be a sequence, right? Let's say machine translation. You are given a Hindi sentence and the output would be English sentence. Let's say summarization. You are given a longer document and your task would be to basically generate a shorter document, right? These are all sequence to sequence problems, right? It can be many to many, it can be many to one, it can be one to many, and so on and so forth. Many to many sequence to sequence model. Sequence to sequence, the term can also be abbreviated as Seq2Seq. Okay, so many to many Seq2Seq problems include summarization, dialogue, right? Many to one, what do you think? Many to one Seq2Seq problem can be classification or no? Huh? So it's not a sequence to sequence as such, because ultimately you are generating a label, but I mean you can think of it as sequence to sequence. It also depends on the way you map it. What is one to many? Example of one to many? No, speech is a sequence to sequence. Speech generation, music generation. What's the input? Input will be a prompt, right? Or so that is many to many. What about image captioning? Your input is an image, and output is a text, a sequence. Of course, you can say that. I can basically flatten the image, make a matrix or whatever, right? That will be a many to many, but high level, this is one to many. Okay, so let's look at this machine translation problem for the time being. In a sequence to sequence model, what we do, since there are two sequences involved, input and output, we will use two RNNs, right? One RNN will process the input, another RNN will process the output. Okay, let's say this is the French sentence. I'm not able to pronounce it at all. I don't know French. Let's say this is the French sentence, and you use a simple RNN, right, to encode the sequence. And let's say this is the last hidden state, right? And this is your output. The output, the translated version of this French sentence is he hit me with a pie. Okay, so the last state of the previous RNN will be fed to the first state of the output RNN, and the remaining process will follow. Now, if you look at this thing very carefully, where is the loss we are computing? So, we are computing the loss at the output hidden state, at the output RNN. This is the output RNN, right? Now, look at the timestamp. So, here, let's say when you allow, so this is the input, right? Ideally, the first input of the first hidden state will be a start symbol, right? And it should be able to generate the next word, which is he, right? Now you pass this he to the next hidden state, it will generate something. Last day I mentioned something called teacher forcing, right? What is the teacher forcing? In teacher forcing, I, instead of feeding he, let's say here the model generates C. So ideally I should feed C, and then I will see what the next word is going to be, right? This is a normal process, but in teacher forcing, I will feed the actual input, right? For example, even if it generates C, I will feed he in the next state, right? Which is kind of a cheating, but this is it. I mean, it turned out to be much more effective in at least training the model. During inference, you can't do this, but during training you can do. Okay, so at this stage you will have some error, at this stage some error, and so on and so forth, right? Look at this. So here you have an error J1, error J2, J3, J4, J5, J7, right? And the total error is basically sum of this. This is the total error, and you normalize it by the number of output tokens T, okay? And then when you do back propagation, right? So this loss will affect all the hidden states. This is end-to-end training. This is called end-to-end training. End-to-end training. Okay. So this error will be back propagated, and all the hidden states in the decoder as well as encoder will be updated. So the input RNN is called encoder, and the output RNN is called decoder. And this is end-to-end training. Clear? Okay, and how do we do this back propagation? We'll use BPTT, back propagation through time. Okay, now if you think of this sequence to sequence problem carefully, this is essentially a conditional language model. Why this is a conditional language model? What is it conditioned on? It is conditioned on the input, right? So X, let's say X is the input. Here input is the, in case of machine translation, input is the French sentence and the output is the English sentence, right? So you are basically computing this probability. So this is, now if you think of Y as Y1, Y2, Y3 ... So the first probability that you are computing at the first hidden state, right? What is the input there? The input is the final hidden state of the encoder, right? So that is X. But you have already processed the entire input sentence, right? So probability of Y1 given X, the next one, this one, what is this one? This is probability of Y2 given X and Y1, right? And so on and so forth. The last one, the last word will be probability of Yt given Y1, Y2, Y3 ... Yt minus 1 and X, right? So conditioned on the generation, the tokens that you have generated so far and the input token, okay? So now when we decode this, how do we decode this? During the inference stage, can somebody tell me, let's say the model has been trained, okay? How the model is trained? I think it is clear, right? How the model is trained? We'll do teacher forcing, right? And we will compute the loss at every timestamp, right? And then we backprop the entire loss end to end, okay? And you do it for all the machine translation pairs. Now during the inference stage, what you do? you are given a, now since there are two in RNNs, encoder and decoder, how many weight matrices are there? So in encoder, how many weights are there? There is this WH, right? There is this WE, and there is this U. So U is not there in the encoder. U is there or not? What is U? The U matrix was the linear projection matrix, right? That is not there in the encoder, because at the encoder stage you are not predicting anything. So you need a WH and a WE. What is WE? WE is the weight matrix corresponding to the embeddings. And at the decoder stage, what are the matrices? WH dash, WE dash, and U. Okay, and these matrices are trained, are learned during the training time. Remember, the embeddings, right? The embeddings that you are using here are different, because input is a French sentence, output is an English sentence. The embeddings are different, right? Let's say if it is a summarization problem, then the embeddings will be same, because the languages are same. Okay, language is same. Okay, so now during the inference time, what we'll do? We are given the French sentence. We pass it to the encoder, right? We will use these matrices. Using these matrices, we will get the final hidden state of the encoder, right? That hidden state will be given to the decoder, and in the decoder, I already know WH dash and WE dash, right? So based on that, I will generate this hidden state, the first hidden state of the decoder, right? And then I pass it through this linear layer U, followed by nonlinearity. It will project it to a 1 million dimensional vector. 1 million is the size of the vocabulary, right? Now, so it will project it to a 1 billion dimensional probability vector. Then you sample one token from the probability, right? And the hope is that the token which has maximum probability will be sampled. So let's say you sampled he, okay, and then you feed here, it will generate heat. You feed. So when I say I feed he to the next layer, what does it mean? It means I feed the embedding of he to WH. This WH dash is the same for all the tokens that you are generating in the decoder. In a greedy decoding strategy, instead of sampling the token based on the probability, I will choose the token which has the maximum probability. I will not do any sampling. Okay, this is a greedy decoding. So what is the problem with greedy decoding? The problem is that, let's say if you made a mistake at any point, you won't be able to recover it. Let's say you wanted to generate so you wanted to generate he hit me with a pi, so you generated he, and then you generated hit, and suddenly you generated a, but you should have generated me, isn't it? You won't be able to backtrack, because it has already been generated. The a will be fed to the next state, and in the next state something else will be generated. This is the problem with greedy decoding, right? Now tell me, what do you think? Like, how do you address this problem? Is it possible to do some sort of exhaustive search to address this problem? So now think about it. Instead of generating one token at a time, right? If I could have generated V number of tokens, what is V? V is 1 million, right? I generated all V number of tokens. Now again, for each of this V tokens that I've generated, I pass it to the next layer. It will generate again V tokens, and so on and so forth, right? V tokens and so on and so forth. Is it possible to do that? It is not possible to do that, right? let's say if it is possible to do, what would be the complexity? There are t number of timestamps in the decoding state, right? Stage, and let's say v number of possible tokens that you can generate. How many possible branches you need to keep track? B to the power t, right? B to the power t. This is extremely exhaustive. Okay, so how to then solve this problem? Let's not make it that exhaustive. Let's squeeze it as much as we can, and to basically squeeze the entire thing, we'll use something called beam search. Okay, in beam search, what we do, the idea of beam search is very same as the exhaustive search. Only difference is that instead of keeping track of v possible options, I will only keep track of k possible options, where k is the size of the beam, right? It means that instead of generating only one token as we did for greedy decoding, or v tokens as we did for exhaustive search, I will generate k tokens. K can be 5 or 10, whatever you set the value of k. Okay, so at every stage here, let's say I generate k tokens. Now from each of these k tokens, I further generate k tokens, and so on and so forth. So complexity is still significantly high. Complexity is still k to the power t, isn't it? But k is much smaller than v, right? And you can decide the value of k. Okay, so now what we do, now think about it. You generate a token here at time t, right? You generate, it's a k number of tokens, right? Token 1, token 2, k number of tokens here, okay? And from each of these tokens, you again further generate k number of tokens, and so on and so forth, right? And then you stop at certain point, right? When do we stop? When do we stop the decoding phase? When do we stop? I give a French sentence. When this decoding stage will stop? When it generates a token called EOD. There are two tokens, special tokens, start and EOD, end of sentence or whatever, end of decoding, EOD, right? Full stop basically, right? So this is one way of basically stopping the decoding phase. There are other ways also. So each of these branches, right? So let's say this branch will lead to end of token. This branch will also lead to end of token. This branch will also lead to end of token. So there are multiple branches, right? Each of these branches is called hypothesis. Why hypothesis? Because we do not know which of this hypothesis is correct. Which of these branches is correct. Therefore, this is called hypothesis, right? So now which hypothesis I will choose at the end? I will choose a hypothesis whose score would be higher. And how to measure this score? The score is essentially the log probability of the sequence that we have generated so far. Clear? So two things I mentioned. One is the value of k, right? We decide a k, and then every hypothesis will be assigned a score. Okay. Now let's look at example. This is an example. So a beam search of size 2. I start with this special token start. This is the decoding stage, inference time. Decoding stage, inference time, not the training time. Remember this. Let's say the value of k is 2. So I have generated two tokens, I and he, right? And what is this probability? This log probability. How do we get this probability? We will get the probability from the distribution, isn't it? Because we have this linear layer and then softmax, right? We will get the probability from the distribution, and we take the log probability. Log probability is basically we sum all the log probabilities, which is same as multiplying all the probabilities. Now since this is probability, it will range between 0 to 1. The log of this will be negative, right? So all these negative numbers will be added, and I will choose that hypothesis whose value is maximum. which is less negative. Here the score till this point is 0.7, minus 0.7, minus 0.9. Which one I will choose? Which one I will choose? I don't need to choose because the value of k is already 2, right? Let's explore this further. Now from he, the next two tokens can be heat and stark, right? From I, the next tokens can be was and got. So till this part, what is the probability? So at this stage, the probability is the probability of this plus the previous one, right? So the total probability is minus 1.7. Here the total probability is minus 2.9, minus 1.6, minus 1.8. So out of this, how many will choose? We choose only 2. So which 2 will choose? We will choose the highest one, right? To maximum one. So one is minus 1.7, the other is minus 1.6, right? And then we explore further. So heat will generate further. From heat I will generate A and me. From was I will generate heat and stark, and so on and so forth. Here again from this 4 I will decide 2, right? Now look at here, this branch is gone, right? Now only I am exploring the top branch. From each of these again I will generate 2, right? And so on and so forth. Again these 2 will be selected. From these 2 I will generate 2 from each, right? This 2 will be selected, and this, right? Let's assume that here after this the EOD is generated. Okay, so among this, which one is the maximum? The maximum one is this one, minus 4.3. Then I will backtrack, and this is the backtracked, right? So I will generate this. The problem here is longer hypothesis will be penalized. Shorter hypothesis will be given more advantage. Why? If it's a longer hypothesis, then you keep on adding multiple minuses, or basically you are multiplying so many probabilities, which will lead to lower probability value. Let's say you had one hypothesis where there are only 2 tokens versus you have an hypothesis where there are 10 tokens. So which one will be preferred? Let's say both these hypotheses were successfully led to a end of token, right? Which will be preferred? The shorter will be preferred because of this one, right? So what I do here, we will normalize the score by the number of tokens it has generated. So if a longer token is generated, right, I will normalize it by the number of tokens. Shorter token, again number of tokens. That will nullify this one. Clear? Is clear? Okay, so sequence to sequence problem was very popular, right? Sequence to sequence model was very popular in 2014. In fact, it turned out to be one of the popular models which basically outperformed all the statistical machine translation models that were out there, right? 40 years of statistical machine learning history, statistical machine translation history, right? Suddenly the sequence to sequence model outperformed all the statistical models. Okay, and then in 2016, right, people noticed that some more tweaks or some more modifications can also be done on top of sequence to sequence. Okay, in 2016 a new method was proposed which is called the attention. Okay, now let's look at attention here. So now so far sequence to sequence is also RNN. There are 2 RNNs, right? There are 3 problems which still persist. What are the 3 problems? The first problem is you can't access all the tokens in parallel, right? The first problem. The second problem, if you think about it very carefully, the sequence to sequence model essentially considers every each pair of interactions, right? Let's say hidden state t, hidden state t plus 1, this interaction, hidden state 1, hidden state 2, hidden state t plus 5, hidden state t plus 6, every consecutive pair of interactions are considered in a similar way. So the interaction distance is considered as linear. Right? So the way we treat 1 versus 2, the way we treat t I minus 1 t, we will treat the same way let's say t plus 5, t plus 6. The third problem is very important. The third problem is called the bottleneck problem. What is the bottleneck problem? Let's go back. So the bottleneck problem says that, look at this one, okay? So this guy, this is the final hidden state of the decoder, right? So this input is fed to the, this is the final hidden state of the encoder. This input will be fed to the decoder, right? The decoder has access to only this hidden state, right? For the decoder, this is the input. Decoder doesn't have access to these hidden states, right? So this guy has a lot of responsibility of remembering the entire input sequence, right? So there is a bottleneck on this in terms of remembering the entire sequence of the input, right? If you are not able to compute it properly, you will not be able to process it. But think about it very carefully. The word he corresponds to the word il. The word pi corresponds to the word this, right? But at this time, at this stage, this hidden state has no access to the first hidden state of the decoder, of the encoder. So due to vanishing gradient problem, due to other problems, right, over smoothing and etc., it will happen that this hidden state will essentially forget about the first hidden state, right? And when you come here, this guy will completely forget about this one. So instead of this, if we had a direct connection from decoder to encoder, right, that could have solved this problem. Maybe let's say there's a direct connection from he to il, from a direct connection from pi to this one, right? Then that could have solved the problem, because through these shortcuts, right, information can move from encoder to decoder. Okay, so this is the philosophy of attention. So attention, let's look at the attention. It's not a complicated architecture though, simple. I already mentioned about this bottleneck problem, right? So what is attention? The core idea here is that on each step of the decoder, we use a direct connection to the encoder to focus on a particular part of the source sequence. So let's look at the architecture first, and then we will understand. Let's take a desi example. Okay, हम बाजार गए थे. Okay, and you want to convert this Hindi to English. So in attention, what we do now, this is my encoder state, right, and this is the final hidden state of the encoder. The first hidden state of the decoder, this will have access to all the previous encoder states, right? And how do we do that? Here we introduce a concept of query and value. Each of these decoder hidden states will act as a query, and each of the encoder hidden states will act as a value, right? So the decoder hidden state will basically check which of the encoder hidden states will be relevant for that decoder state, right? Relevant means which encoder states will be helpful for the decoder state to generate the correct output. Okay, how do you do that? So let's first look at the computation. So this is my query and this is value v. So what I do, I'll first measure the similarity between query and value. And how do we measure this? We measure this using simple dot product. So this vector and this vector will be passed through a dot product, right? And we get a scalar here. Scalar, this vector and this vector will pass through a dot product, right? And then similarly, this is my query, this is V. So each of the decoder state will basically be used to do the dot product of every encoder state separately. So this is the second dot product, third dot product, fourth dot product. What are these dot products indicating? They are indicating the similarity, right? So these are called attention scores. All of these elements are scalars, remember this. From attention score, I pass them through softmax. Softmax will produce a distribution, and this distribution is called attention distribution. Let's say this is P1, this is P2, this is P3, and this is P4, right? And let's say this is V1, V2, V3, V4. V1, V2, V3, V4 are vectors. P1, P2, they are scalars, right? And from there, from this computation, what I do, I will generate something called attention vector. Attention vector, right? What is the attention vector? Attention vector is the weighted sum of the encoder states. Weighted sum of the encoder states. And what are the weights? Weights are the probabilities. So attention vector will be P1 and the corresponding vector V1 plus P2, V2 plus P3, V3 plus P4, P4. This times this plus this times this, right? And plus so on and so forth, right? So P's are the weights. So what is this vector? This vector is the weighted sum of the encoder state. And how these weights are computed? The weights are computed based on the similarity between the decoder state and the encoder states, right? Remember, these weights will be different when I move to the next decoder state, right? So I got this attention vector. I already have a hidden state here, right? And the attention vector here, which I compute. And then, so this is attention vector and this is the decoder vector, decoder hidden state. I just concatenate them. So at this time, at timestamp 1, hidden state is H1, right? Attention vector is, let's say, A1. I concatenate them, right? And then what I do? I pass it through a linear layer U followed by nonlinearity, and it will generate a probability. So instead of passing the hidden state directly to the linear layer, I will pass this concatenation of hidden state and attention vector, right? So similarly, for the next decoder state, this is my Q and this is my attention distribution. Now look at this distribution and the previous distribution. They are different, right? Now if you look at the distribution carefully, to generate the first output token of the decoder, look at the probability. Which encoder was useful? Which encoder state was useful? The first one was useful. Therefore, the corresponding probability was high. To generate the second input had, which one is useful? The last one was useful. To generate the third one was useful. To generate the fourth one, the second one was useful, right? And how do we get this usefulness? From the probability, the dot product probability. This is clear? There is no bottleneck problem here. Why there is no bottleneck problem? Now we have a shortcut from every decoder state to all the encoder states. Every decoder state can access all the encoder states. Clear? So this is attention. Now tell me, due to this attention, due to incorporating the attention concept, did I incorporate any additional parameter? Answer me, quick. No, there is no parameter involved. What are the parameters here? The parameters are same: WH, WE, WH dash, WE dash, and here U. That's all. There is no U here. There is no U here. Attention score, attention distribution. There is no U here. So this is vanilla attention. Okay. Of course, there are modified versions of attention I will discuss, but this is the vanilla attention. Okay. So let's look at the equation once again. The attention equation I have already mentioned. So H1, H2, H3. Look at this equation, right? H1, H2, H3, Hn. These are the hidden states. Hidden states of the encoder E, right? What is ST? ST is the hidden state of the decoder at the TH time period. So ST will basically access all the hidden states of the encoder. So ST H1, ST dot product H1, right? ST dot product H2, and so on and so forth, right? So we generate these numbers. These are dot products. These are attention scores, right? Let's say this is ET. Attention scores will be passed through softmax. So alpha T is the attention distribution, which will act as weights, right? So alpha T will then be then act as a weight for each of these hidden states of the decoder. So alpha I, HI, right? T ranges from 1 to n. What is AT? AT is the attention vector, right? Then AT and ST. ST is the hidden state of the decoder. These will be concatenated, right? And then this will be passed through the linear layer. Attention is great. Why? Attention not only gives you a shortcut from decoder to encoder, it also gives you many additional information, right? What are the additional information? It reduces the problem of bottleneck problems, right? I already mentioned, okay, bottleneck problem will not be there. It will also help address the vanishing gradient problem. Why? Because now there's a shortcut, right? One gradient is moved through this, one gradient is moved through the shortcut. Very similar to skip connection, right? The most important beauty of this attention is that it gives you interpretability. For example, here, based on this distribution, you can say that to generate the last word of the decoder, second word was more responsible. You will not get this kind of information from a vanilla RNN, right? So if somebody tells you, can you explain that why you generated this? You can say that look at the probability. So this is my attention map. So my French inputs and the English outputs, and you see, so this entry, so each of these rows indicates, okay, attention distribution. If one entry is dark, it means the probability is high, right? So to generate the word he, the word ill was responsible. To generate the word with, a and pi, the last word of the encoder was responsible. Therefore, it's dark, right? So from the attention matrix, you can identify the portions which are responsible. So this will give you an alignment also. So in a statistical machine translation model, which I did not discuss, there are three components. Two components. One is the translation. So you basically, so main bazaar ja raha hu, I am going to the market, right? So it is not one-to-one translation. If you think of it carefully, this is not word-by-word translation. Sometimes we need to change things here and there. So in statistical machine translation, there are two components. One is this one-to-one translation, and then you do some alignment. So alignment will rearrange the token, right? So for the alignment, you need a separate model. But here, you do this alignment for free due to this attention. By the way, sometimes there are papers which claim that attentions are used for interpretability. There are papers which claim that attention can't be used as can't be used to for interpretability. This is debatable, but therefore I said it gives some interpretability. So I discussed attention with respect to sequence problem, right? But attention is not restricted to sequence problem. Attention can also be used in other models. You can use attention in normal RNN, for example, right? So in general, you can think of this attention as a generic concept in deep learning, where you have a query and you have some values, and you want to measure the importance of query with respect to all the values, right? You can use attention. You can also think of an attention, the attention vector that you generated. Remember, attention vector is one vector that you generated, right? For every decoder hidden state, you generated one attention vector, right? So attention vector can also be thought of as the summary of all the value vectors. Think about it. Attention vector can also be considered as a summary of all the value vectors. In our case, the value vectors are encoder of hidden states. It's a summary, right? Irrespective of the size of the encoder layers. How many encoder layers? Let's say there's a sequence where there are 100 encoder layers. There is another sequence where there are 10 encoder layers. Irrespective of the size of the encoder layers, you can always generate one vector, attention vector, right? So it basically, you can think of attention as a summary of the value vectors. You can think of attention as something which can squash the entire encoder states into a single vector. Okay, why I said all these things? Because when you apply attention to some other problems, you need to understand all these factors. These are some variations of attentions. The one that I discussed was a simple attention method, right? I basically discussed this one. This is called dot product attention, right? This is the one that I discussed. You can also think of some sort of parameter, right? Because we have a lot of data. We will be very happy if we are able to add more parameters, right? So you can also add a parameter between the query and the value, right? What you can do, you can pass the query to parameter matrix, right? You can also pass the value towards the same parameter matrix. It's basically a bilinear product, right? And then it will generate some vector. You can also think of doing some complex formula. For example, you concatenate the query and value, then pass it through a linear layer, right? Some non-linearity, then pass it through another linear layer, right? That will give you a vector, right? The transformer paper, they use something called scaled attention, scaled dot product, where we take the dot product and this dot product is normalized by the size of the vector. What is mod k? Mod k is the size of the value, right? And you take the root of this. So this is scaled by the size of the vector. There is no intuition, by the way. I mean, these are different hacks, engineering hacks. Okay. So this is all about attention. We stop here, and in the next class we will discuss self attention and then the transformer model. Okay. Thank you.